Okay, so the last thing in 8.3, so we did mean, median, mode, we did mean or average with frequency tables, and so the last thing is using probabilities. Alright, so finding a probability distribution and using our probabilities instead of a sample space, instead of actually polling people or running an experiment looking at the data. And so what we do is when we have a probability case, it's making a prediction about the population. We don't actually poll people. We don't actually run the numbers. All right, what we do is we base it on the chance, the probability. And so it's called the expected value of our finite random variable. Just to kind of give a simple example of that, if we took a coin and flipped it 10 times, based on what we understand about coins, is that, well, we would expect half of them to come out heads and half of them to come out tails, right? Based on our probabilities. So we would expect 50% of them to be heads and 50% of them to be tails. So 5 out of 10s to be head, 5 out of 10s to be tails. Now, if you actually did the experiment, would you be guaranteed to get 5 heads and 5 tails? No. But if we did the experiment many times, so suppose I flipped a coin 10 times, 1,000 times. Alright, sometimes I got more than 5 heads, sometimes I got less, sometimes I might have got 5 heads. And I averaged out all of those outcomes. The average should be pretty dang close to 5. 50% of them come out heads. The bigger the sample space, the bigger the experiment, the closer to that theory I get. It's called the law of large numbers. Now, again, in this class, we just hit the basics, so we don't go through the law of large numbers. If you actually take a real statistics class, they'll talk about this in much greater detail. But basically, that's what it is. So this is our expectation of the population. This would be our expectation if we did the experiment 100,000 times. Sometimes we get 3 heads, sometimes we get 10, sometimes we get 5, sometimes we get 4. We averaged them all out. The average should be 5. We're pretty darn close to 5. Alright, so again, it's what we expect the value to be. What we expect, it predicts the population mean based on probability and the law of large numbers. Right, flip the coin many times. We would expect the average to be 5. On average, we would expect 5 heads to come out. Half of them to come out heads, based on probabilities. Again, my note there is it's what we expect to get, not what we would actually get if I did the experiment. Now, I might get 5 heads, I might not. It's just an average. It's what I would expect to happen. Alright, so finding the expected value with probabilities. Alright, so x is my finite random variable, takes on any values between, whatever it is I'm looking at, 0 through 10, 1 through 8, whatever my x values run into. Alright, what you do, and again, this is a formula, and I'm going to go through it one time just because it's good for you to understand where the formula comes from, but you don't really have to memorize the formula. We will be just using the stats key on the calculator. Alright, so what it is it adds up the probability of each outcome, right? We take each outcome and its chance of happening and add up all those cases. So that's what the mean would be. The probability of the first event happening would be the event times p. The probability of the second event happening would be that event times its probability. And then this is sum, so I'm going to add up all of those probability cases. When I add up those probability cases, those would be my expected or predicted population average. All right, so remember, the expected value, which this is the notation that you have to recognize, E of x, is expected value, and it predicts the population average. Alright, so it's what we would expect the population average to be if we did the experiment many times. We took lots and lots of samples over the entire population, again, using probabilities. So the first example, the random variable x is the amount a person wins in dollars after purchasing a single raffle ticket, right, which costs $5. So x represents how much you can win. So you're in a raffle. There are 3 possibilities. You win nothing, which is $0, right? That's the first x variable. There's a $50 prize, and there's a 4% chance you win the $50 prize. Or there's a $100 prize, and there's a 1% chance you win the $100 prize. We want to know, well, if you bought a bunch of raffle tickets, and not just one, you bought many raffle tickets. Some of them would be winners, some of them would be losers, some of them you'd win nothing, some of them you'd win 50, and some of them you'd win 100. What would be your average winnings? If played this a lot. If you did a lot of raffle tickets, what would you win on average? And so this is based on probabilities. We're predicting how much we would win on average. And so what you do is you take x times the probability of x. So that's the first thing I'm going to do here. So the first one is 0 times its probability, which is 0.95, which comes out 0. The next one would be 50 times 0.04, which comes out 2. The next one would be 100 times 0.01, which comes out 1. Right, then it's the sum of those, right? It's the sum of x times its probability. Sum means add them up. And so it would be 0 plus 2 plus 1. And so our expected average, the expected value, would be 3. Which means if we bought many raffle tickets, all right, not just one, we bought a lot. All right, many, large number, large set. The winnings would average out, the winnings and losses, an average of $3 in winnings. Again, that would be the average. I can't win $3. I'm going to win nothing a bunch of times. 95% of the time, nothing. I'm going to win $50 4% of the time. I'm going to win $100 1% of the time. When I add up all of those outcomes, those percent chances, it should, and this would be what we would expect to happen, not guaranteed to happen, but this would be our expectations. We average out our winnings and our losings, and it would average out to $3. And again, this is if I bought a bunch of raffle tickets. And this is the way it works, right? So you actually come out behind, right? If you bought your raffle tickets for $5 a piece, for each raffle ticket, the average winning's $3, well, you're out $2 per raffle ticket. Right? So again, it's based on the law of large numbers that you buy a bunch of raffle tickets. Now, if you bought one raffle ticket and you won, you don't fall into this category. It's buying more than one raffle ticket. All right, so the next example I'm going to show with the calculator. So that was the by hand. On the next examples, I'll show you with the calculator. All right, so example 2 we'll do on the calculator. So we want to find the expected value and explain what it means. In order to do that, I need my probability distribution. Expected values based on probabilities. All right, so I need my probabilities. So my x value in my probability represents the lowest value of the pair. So there's all of my pairs in my universal set when I roll 2 dice. All right, there's all 36 outcomes in my sample space. All right, I'm interested in the number that's showing up the smallest. All right, so x is the lowest value. The probability of x equals that number. And so 1 could be the smallest. Whenever 1 shows up at the smallest. Whenever 2 shows up, as long as it's not paired with 1. 3, 4, 5. And actually 6 is a possibility because in the 6, 6 case, it's the smallest number. It's the only case where 6 is the smallest number. Alright, so now the probabilities. 1. 1 is the smallest whenever 1 shows up. Well, these are all of the values where 1 shows up. And if you count that, there are 11 outcomes out of my 36 where 1 is the smallest number. 2 is the smallest number as long as it's not paired with 1. And so all of these would be outcomes where, if you look, 2 is the smallest number in all of those. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 36. 3 is the smallest number as long as it's not paired with, so basically the pattern is it kind of goes over in these little L shapes. Right? 3 is the smallest number in all of those, right? 3 is smaller than 6, 3 is smaller than 5, 4, 3 is the smallest if it's the only one there, and 4 and 5 and 6. And so you count those, it's 7 out of 36. Right? Then the next one would be 4 is the smallest as long as it's paired with 5 and 6, and so those are all the values where 4 is the smallest, which is 5 out of 36. Then 5 is the smallest as long as it's paired with itself and 6, and 6 is only the smallest if it's by itself, 1 out of 36. And so there's all the probabilities if I'm looking at x is the lowest number in the pair. And And so I'm just leaving the fraction. So when I go to plug them into my... So again, I'm going to solve this on my calculator. I'm going to plug it into my calculator. I'm just going to plug them in as the fraction. Right? I want the expected value, which is the expected mean. And I'm going to use the calculator. Now, the calculator gives it to you as x bar, even though technically this is based on the probability, so it would be the mu symbol. But the calculator doesn't change it. It leaves it x bar, assuming that most of the time you're looking at a sample. All right, so just be aware of that. It's the expected average, right? The expected mean. And so on the calculator, it's the mean symbol. All right, so go to the calculator. Clear out what I have there. It's the same place we were plugging our frequency tables in. So go to Stat, Edit, Enter, clear out my previous frequency list. All right, and then in list 1 is going to be the x values. List 1 is always the x values. List 2 is your probabilities. Right? Probability is a frequency. It's the frequency based on your chance of happening. Right? So, right, if you have a 20% chance of happening, well, the frequency is 20% of the time. Right? So it goes into list 2. So if you have list 2, should be your probabilities. All right. So list 1 is your x values, which are 1 through 6. 1, 2, 3, 4, 5, 6. List 2 are your probabilities of getting those. So 1 was 11 divided by 36. And again, type it in exactly. 2 was 9 divided by 36. 3 was 7 divided by 36. 5 divided by 36. 3 divided by 36. And then 1 divided by 36. Alright, so as long as they're plugged in there right, I'm ready to quit. Go back to Stat. It's still one variable statistics. One variable statistics. Select it. And even though it says frequency list, it's probabilities, and frequencies really are I guess probabilities are frequencies. It's frequencies based on your percent chance that it's going to happen. All right, so in list, it should say list 1. In frequency, it should say list 2, and you're ready to calculate. Again, if your calculator is the older version, you have to do list 1, comma, list 2, and then you should find this. And so it's the one at the top, the x bar, and so the average is 2.528. 2.528. So if we did this experiment a lot, so if we rolled the dice many, many times, thousands and thousands of times, alright, so if we rolled the dice many, many times and noted the lowest, so we tallied the lowest number from the pair that we rolled, the average would be expected .528. So sometimes 1's going to be the smallest most of the time. 2's going to be smallest, but once in a while you'll roll 2 6's. 6 is the smallest. If you averaged up all of the outcomes, if you did this like 1,000 times, the average should come out to about 2.5, 2.58, right, on average. So some of them will be more than that, some will be less than that. That's my average. So again, it's okay that it's a fraction because it's an average. One more example of this, and then we're going to do the binomial special case, which will be the next video. Alright, so grabbing the marbles. If you remember from your 8.1 notes, so I'm going to just pull it from my 8.1 notes. If you want to know where I get this following table, it comes from so this is the one we did. We want to find the expected number of blue marbles grabbed on average from this bag of marbles. Alright, where I've got 4 red, 3 blue, 2 greens, 5 marbles selected at random. Alright, set up the probability distribution and solve on the calculator. We already did the probability distribution in lesson 8.1, so I'm just going to write this down from our 8.1 notes. So in 8.1, right, x represents the number of blues in my handful. this is the probability. Right, so I could have 3 blues in my handful, 2 blues, 1 blue or no blue in my handful. And if you remember, this was 15 out of 126, 60 out of 126, 45 out of 126, and 6 out of 126. So if you remember, that's from the 8.1 notes. And so now we're going to, here's my probability, now we're going to set the calculator. So remember, list 1 is always the x values, list 2 is your probability. So you're going to go into your stats. You're going to do your 1 variable statistics. Again, if your calculator's like mine, list should be list 1. Frequency should be list 2. If yours is an older calculator, you've actually got to type in list 1, comma, list 2. Then it'll give you all of the information. It's the very first one on there. Our expected value is our expected mean. Now in the calculator, it comes out x bar. All right, if you do that, it comes out. So I'm going to let you type in your own this time since I've done it a few times on the calculator. So if you type it out, list 1, make sure you're careful, type the fractions in exactly. Take 15 divided by 126, 60 divided by 126, and so on. It comes out to 1.6 repeating, and so I'm just going to round a couple decimal places. 1.67 would be the expected value. So again, if we did the experiment, many times. So we reached into this bag of marble and grabbed out many handfuls of marbles. Sometimes we get 1 blue, sometimes we get no, sometimes we get 3. The number of blue marbles that we get averages to about 1.6. Alright, so on average, so again, it's an average. Sometimes I get, so if I add them up, all the different outcomes, where I get 3, 2, 1, 0, and averaged them, the average should be about 1.67 if we did this a whole bunch of times. The more times we do it, the closer to that average we get. Alright, so that's probability distributions. The very last thing from 8.3 is still looking at probabilities, but it's looking at our special type of probability, the binomial case, and it is done differently than this. And so that's the last set of notes, the last part of this set of notes.